sklearn neural network Bernoulli-RBM. Description: the Bernoulli restricted Boltzmann machine RBM is a generative stochastic neural network that learns a probability distribution over its inputs. It consists of two layers: a visible layer representing the input data and a hidden layer representing latent features. The RBM learns to reconstruct the input data by minimizing the difference between the input and the output of the model. The model is trained using contrastive divergence, which is an approximation of the gradient descent method. Inputs: X a 2D array of input data, where each row represents a data point. Y an optional 1D array of target labels. Outputs: H a 2D array of hidden layer activations. PH give NV a 2D array of probabilities of the hidden layer activations given the visible layer. Activations. Steps: initialization: the model initializes the weights and biases randomly. Contrastive divergence: the model trains using contrastive divergence, which involves iteratively sampling from the data distribution and the model distribution. Gibbs sampling: the model uses Gibbs sampling to generate samples from the model distribution. Metrics: reconstruction error measures the difference between the input data and the output of the model. Free energy measures the energy of the model. Visualization plots: hidden layer activations visualizes the hidden layer activations for different input data points. Reconstructed data visualizes the reconstructed data generated by the model. Fine-tune parameters: learning rate controls the step size of the gradient descent algorithm. N components: the number of hidden units. Batch size: the number of data points used in each training iteration. Epochs: the number of training epochs. Random state: the random seed used for initialization. Uncertainty methods: dropout: randomly drops out units during training to prevent overfitting. Bayesian inference uses a probabilistic approach to estimate the uncertainty in the model. Parameters: challenges and fixes. Challenge 1: the model may overfit to the training data if the number of hidden units is too large. Sample use case that resulted in challenge 1: the model was trained on a dataset with a large number of hidden units and achieved perfect performance on the training data, but failed to generalize to unseen data. Fixes to challenge 1: reduce the number of hidden units. Use regularization techniques such as dropout. Use early stopping to prevent overfitting. Challenge 2: the model may be difficult to train if the learning rate is too high or too low. Sample use case that resulted in challenge 2: the model failed to converge when using a very high learning rate, and the training loss oscillated wildly. Fixes to challenge 2: tune the learning rate carefully. Use a learning rate scheduler to gradually reduce the learning rate over time. Challenge 3: the model may not be able to learn complex patterns if the number of hidden units is too small. Sample use case that resulted in challenge 3: the model was unable to learn the underlying patterns in a dataset of handwritten digits, resulting in poor performance. Fixes to challenge 3: increase the number of hidden units. Use a more complex architecture, such as a deep Boltzmann machine. Challenge 4: the model may be sensitive to the initial values of the weights and biases. Sample use case that resulted in challenge 4: the model converged to a local minimum, resulting in poor performance because of the poor initialization of weights and biases. Fixes to challenge 4: use a good initialization technique, such as Xavier initialization. Train the model multiple times with different random seeds and select the model with the best performance.